Welcome back, dear students. So already we have uh, completed one of the thermochemical methods in biomass conversion, that is combustion. Now in this session we will have a brief idea about gasification, another important thermochemical method in. Now what is biomass gasification? So gasification is a process which converts a carbonaceous feedstock including biomass into combustible gas. So mainly we are converting a solid biomass into a gas, a mixture of gas which is very easily combustible, so that we can use it later or other applications if required. And remember, this gasification can be done to any solid carbonaceous material, not only biomass, even coal. Coal gasification is another important application of gasification. Now these are done in the presence of an oxidant. So normally we can use air, or some case we can use oxygen alone, and steam can be also used. So in some case we can use both air and steam. So like that we can use different types of oxidants for gasification. And the important thing is here, our supply of oxygen will be very much less than the stoichiometric ratio. So we already know the stoichiometric air fuel ratio is the air required for complete combustion. But in gasification we will be supplying less than that, typically around 30 to 35%. And the resultant gas is normally known as syngas or synthesis gas. Shortly it is known as syngas. And what are its major constituents? Major constituent will be hydrogen, carbon monoxide, carbon dioxide and methane. So these are the gas that will be present in syngas. And in this CO2, we know the CO2 does not have any combustion or calorific heating value because it is already a completely burned gas. So our aim will be to increase hydrogen as well as carbon monoxide. So CO2 content should be decreased for getting a good syngas. And some other higher hydrocarbons also will be there, a very negligible percent. But if you are using air, this is syngas mainly used by oxygen as an oxidant. But if you are using air, we know that air we have 79% nitrogen and 21% oxygen. So the nitrogen, high amount of nitrogen will be present in the resultant gas, and they are another term we can call it as the producer gas. So if you are using air only for gasification, that can be used as or called it as producer gas, which contains a large amount of nitrogen also. And this is a typical comparison of syngas and producer gas. So here you can see a syngas is having hydrogen 20 to 30%, but producer gas will be less than that hydrogen content. CO here we have 40 to 60% in syngas, but here it is very less. And similarly CO2 also. And mainly you look at the nitrogen content. So if you are using oxygen for gasification, the nitrogen content will be very less, because it depends on only the small amount of nitrogen in the biomass itself, less than 4% in that range. But if you are using air for this gasification, you can see here around 45 to 50% will be nitrogen. And this will result in the heating value also. You can see here the heating value of syngas is from 9.3 to 14.9. That means more than 10 megajoule per meter cube energy content you will get. But for producer gas it will be between 4.5 to 6. So this is a typical comparison of syngas and producer gas. And what are the different reactions involved in gasification? So gasification means a series of chemical reactions. Some of them will be endothermic, some of them will be exothermic. First one, we have the gasification reaction with oxygen, that is carbon reacts with oxygen, half mole of oxygen to form carbon monoxide, and this is an exothermic reaction because delta H, the enthalpy change is negative. The enthalpy change is the enthalpy of reactant minus enthalpy of product. So that means this is an exothermic reaction because the product is having more energy, more heat is liberated. So this is an exothermic reaction. And we have combustion with oxygen, that is a complete combustion with oxygen also will happen. That is carbon reacts with oxygen, 1 mole of oxygen to form carbon dioxide. Again this is an exothermic reaction, minus 393 kilojoule per mole. Then gasification with carbon dioxide. So carbon dioxide can be converted to carbon monoxide, that is known as the Boudot reactions. So here you can see the solid carbon will react with carbon dioxide to form 2 moles of carbon monoxide, but this is a endothermic reaction because we have the enthalpy value of positive quantity. So this requires heat. So this reaction will absorb some heat equal to this. Now we have, if steam is used as an oxidant or steam is used with air, we have this reaction, that is carbon will react with water vapor to form carbon monoxide and hydrogen, and this is also an endothermic reaction. And another important reaction will be the gasification with hydrogen, that is carbon will react with hydrogen, 2 moles of hydrogen to form methane, and this is an exothermic reaction. And another important reaction, that is the water gas shift reaction. So this is an important reaction, that is the water. So reaction with water, carbon monoxide formed will react with water vapor to form hydrogen and carbon dioxide. This is also an exothermic reaction. Then we have a methanation reaction, that is a methane formation. This carbon monoxide reacts with hydrogen to form methane and water vapor. So you can see the most of the reactions are exothermic, so heat is liberated. A few are endothermic, so that heat can be utilized by these reactions. So these are the important reactions to be considered while studying gasification. Now gasification can be split into mainly 4 steps, that is drying, pyrolysis, reduction and oxidation. So these, any gasifier, these steps will be taking place in different locations and different time. So these are, try to understand what are these process. So first one is drying, means we know when temperature increases the water vapor will evaporate from the biomass, that is known as drying. Then pyrolysis is decomposition. The biomass will be decomposed into different constituents. Solid carbon and volatile gas will be volatilized. Then we have reduction of this component, and with the help of oxidant, oxidation also takes place. So these steps will be there in gasification. So this is the typical block diagram of that. First, our biomass undergoes drying process, moisture content reduces. Then this is a most important one, that is pyrolysis. In the absence of oxygen, our biomass is split into or decomposed into several elements. One is solids, that is a solid char. Then liquid also will be there, tar and bio oil, etc. Then gas, volatiles will be released like carbon monoxide, hydrogen, etc. And this will undergo reduction reactions and oxidation also. Different reactions we have discussed. And the char, solid char will also have some reactions, combustion of solid char, etc. So these are, we can see 2 simultaneous pathways after pyrolysis. One is mainly this gas, the volatile gas will undergo different combustion, water gas shift reaction, etc. to yield different products. And simultaneously the solid char will also go different reactions. That is why we have two pathways here. So this is the overall picture of gasification. And mainly what are different types of gasifier? We have fixed bed gasifiers where the bed is stationary. Mainly we have updraft gasifier and downdraft gasifier. Then we have fluidized bed gasifiers. So in that mainly we have bubbling fluidized bed and circulating fluidized bed, and we will have a double fluidized bed also, but mainly we have only discussed these two, that is bubbling fluidized bed gasifier and circulating fluidized bed gasifier. So these are already we have discussed in combustion. While studying combustion also we have discussed the bubbling fluidized bed combustor and circulating fluidized bed combustor. So like that we have to discuss. And another two most modern type of gasifier is, one is Entrained flow gasifier and plasma gasifier. So plasma gasifier is a very recent innovation in this area. So we will just discuss one by one. So first we will discuss the updraft gasifier. So this is a figure of updraft gasifier. So you can see here the air. See here the air is coming from the bottom and going up, and our fuel or biomass is feeding from the top. So they are in counter current motion. So the solids will be moving like this in this direction. You can see the solid will slowly move through this combustion chamber, and finally the ash will be collected here, and the gas or the air will be moving in this direction, and our syngas will be collected from the top. So in updraft gasifier, that is why it is known as updraft, the air is moving up. So biomass feed is added from to the top of the bed, and while air enters through the bottom. So they are in counter current direction, or the movement of solid and gas. The solid is moving from top to bottom, while the air and the gas are moving in the upward direction. So they are also known as a counter current gasifier because they are in opposite direction. And these are the first developed gasifiers and very easy to be fabricated and inexpensive. And they also offer high carbon conversion efficiency. How much percentage of carbon is converted to gases, and the gasifier efficiency also high, and they have a low dust level in syngas. So these are some advantages of this updraft gasifier. But the problem is the syngas will contain about 25% water insoluble tar. So the tar formation is an important thing we have to face while designing a gasifier. The tar is a compound that is insoluble in water, is in liquid state. So once the tar is formed, they will block the passage of these gas, solids, etc., and ultimately it will affect the performance of gasifier. So in this updraft gasifier, the main problem is our syngas contains around 25% of tar, and there is a chance of this due to this tar formation and also the clingering, bridging, etc. So these are some harmful phenomena happening in gasifier. Clingering is due to the ash, agglomeration of ash and blocking of that in different pipes and other accessories. So all these things can happen in updraft gasifier. So that is why we have to think about some other gasifiers. And a typical particle size for fixed bed gasifier, we have fixed bed gasifier has some high range of particle size, that is some 50 to 150 millimeter. That means a 1.5 centimeter up to 1.5 centimeter particle size you can use, with a moisture content of 10 to around 60%. So their particle size is comparatively high compared to other entrained and fluidized bed gasifiers. Now we will go to the downdraft gasifier. So here you can see what is the difference here. Yes, the air is fed in sideways, not from the bottom. So we will have a small venturi like structure here in this region, and air is sideways, the air is fed, and the fuel is fed again here at the top. And one thing you can notice here is the syngas is collected in the bottom, not at the top. In the updraft gasifier, the syngas was collected here at the top, but here it is in the bottom. So downdraft gasifier, the feed enters the top, but air will be entering from the sides. And what about the flow direction? Here the solids are moving downward and the gas also are moving downward. So here you can see the air and syngas are moving downward. The biomass and the other ash etc. also moving downward. So this is a concurrent flow type fixed bed gasifier. So remember, updraft gasifier is a counter current flow gasifier, whereas this downdraft gasifier is a concurrent flow fixed bed gasifier. And if you see these regions also, we have some difference. So in updraft gasifier we have drying pyrolysis, same as this order, but after that we have reduction, then oxidation. So because in updraft gasifier the air will be first in contact in this region, so that is why we have reduction, then combustion or oxidation zone. But here you can see in downdraft gasifier the reduction comes only after oxidation, because the air is supplied directly here, not at the bottom. So we will have the oxidation zone here. So that will have some slight difference in the product also. And this downdraft gasifier are very much suitable for very dense and high quality feedstocks. So high density feedstocks like briquettes, wood chips, coconut shell, etc. So that is a major difference. In updraft gasifier we are using not that much low high density biomass, but here these are types of gasifier. Downdraft gasifier is more suitable for high density biomass like briquettes, wood chips, coconut shell, etc. And another important advantage is here the tar content will be very less compared to updraft gasifier. So in there the tar formation was the main issue, but in downdraft gasifier this tar content can be considerably reduced. But the feedstock of this gasifier should have low moisture and ash content. So that is why we have to use these coconut shell, briquettes, etc., because they are having a relatively less ash content, and moisture also should be less compared to updraft gasifier. And they are very much suitable for small scale engine application. So if you have to develop a gasifier for some IC engine application, this downdraft gasifier will be very much suitable. But the problem is these fixed bed gasifiers, that is both updraft and downdraft, they are not suitable for scale up capacity. So if you want a very large capacity gasifier, these fixed bed gasifiers are not that much applicable. And here also we have chance of clinkering, bridging, etc. The problems with ash agglomeration, fusion of ash, etc. will happen here also. Now we will go to the next fluidized bed gasifier. So already we have studied the fluidized bed combustors. So these are very much similar to that. So in fluidized bed gasifier, we basically what we are doing, we will be suspending the bed material and as well as these biomass particles and oxygen rich, we use with the help of a oxygen rich gas, that is air, with the help of air or oxygen, etc. We are suspending this or converting this into a fluidized state. So even though they are solid particles, they will behave as fluid with the help of this gas supply from the bottom. So this is a typical fluidized bed gasifier. We have biomass feed from here, and this biomass with bed material. It will be suspended in state with the help of this air supply or oxygen supply from bottom, and syngas will be collected from the top. Ash will be taken from here. So here you can see the advantage is you can see the temperature. If you see the temperature profile of fluidized bed gasifier, they are almost constant. So now, but in updraft and downdraft gasifier, we will have a very steep increase and decrease in temperature. They are not uniform temperature along the reactor. But here you can see they are more or less same from here, this feeding point to the ash collection point. And we can use very much less particle size, 20 mm. Less than 20 mm is mostly used. The moisture of 5 to 60%. And here we know the biomass enters at the side of the reactor. The steam and the other oxygen enters from bottom, and there helps to convert this bed into a suspended state so that it will be in fluidized. And the main advantage is the mixing. Due to this proper mixing and heat transfer, there will be uniform and moderately high temperature throughout the gasifier. And here we have two main classifications, that is bubbling fluidized bed and circulating fluidized bed. This is known as BFB gasifier, bubbling fluidized bed. Another one is known as CFB, that is circulating fluidized bed. So this is a typical bubbling fluidized bed reactor, you can see here. But here the important thing is the air velocity will be not that much high, and we are not recirculating any bed material and other particles to the reactor. So we will have the biomass, the gasifying agent, and the bed materials, and the gas will be goes through here, and but we will separate some ash only from this separator. So bubbling fluidized bed gasifier is one of the popular design, and mainly they are applicable to medium scale application like 25 megawatt or around that. Less than 25 megawatt we can use this BFB gasifiers, and mainly it consists of a reactor vessel where we are introducing a gasifying agent, that is here from air or steam upward, and the velocity of this air or steam will be 0.5 to 1 meter per second. So it is not that much high, less velocity is used, that is 0.5 to 1 meter per second velocity, and that will agitate the bed material and it will be converted into a fluidized state. And here we have the ash is separated from the downstream of the syngas. And the advantage of this BFB is they have the high carbon conversion efficiency, and that is the the major disadvantage is these gasifiers have less carbon conversion efficiency due to the mixing issues. So that is the problem with this type of gasifier, they have less carbon conversion efficiency. And another thing is the oxidation spots due to slow oxygen diffusion, so that some diffusion problem will be there. So in order to reduce this problem, we have this circulating fluidized bed gasifier, that is advanced version of this. So here we have a separator, cyclone or whatever it is, and these solids will be again here we are using very high velocity, that is the one difference, and due to that some bed material also will go with the gas. So we have to separate that bed material and return it to the reactor. So that is the main difference in circulating fluidized bed. So in this circulating fluidized bed, the gasifying agent is introduced upward with a very high velocity. So here you can see the velocity is 3.5 to 5.5 meter per second, more than bubbling fluidized bed. In bubbling fluidized bed we have only around 1 meter per second, in that range. And here the biomass is fed from the side. So biomass is fed from here and mixed with hot bed material and it is dispersed along the vessel, and solids leaving this riser will be separated with the help of the cyclone separator and again return to the bottom. So that is why it is known as a circulating. So again we are circulating the bed material that escaped to the with the gas. And the main advantage is this CFB design overcomes the disadvantage exhibited by bubbling fluidized bed, and due to the better gas solid contact here and absence of bubbles, this prevents the gas from bypassing the bed. So this is an advantage compared to our circulating bubbling fluidized bed. So bubbling fluidized bed, we will have a lot of bubbles, gas bubbles, and but here we will be without an absence of bubbles will have more advantage, and heating rate is also higher due to the recirculation of solids. So here we are recirculating the bed material back, the hot bed material back, so that will increase the overall heat transfer rate of the gasifier. Hence we have an increased gasification and carbon conversion efficiency, and tar production also less. So these are overall advantages of this circulating fluidized bed compared to bubbling fluidized bed. So circulating fluidized bed will have more carbon conversion efficiency and more gasification efficiency and less tar content, and all these are advantage of this over BFB gasifier. Now we have another two more gasifiers. One is the Entrained flow gasifier. So this is a typical Entrained flow gasifier. What here you can see the biomass is fed from top, as well as our gasifying agent, the oxidant also fed from top. So this is having a temperature distribution of this, and this is having a very high temperature. So if you look at fluidized bed gasifier, its temperature will be around some 900, 400, 600 to 900 degree, around that. But here you can see its temperature is around 1400, higher temperature. This operates at higher temperature. So in entrained fed gasifiers, the main difference is here the feed as well as our oxygen or steam etc. are entering from the top, and syngas exit from the bottom. So that is the difference here. But in fluidized bed, what is the difference? Fluidized bed, biomass will be entering from sides or top, but our air and steam will be entering through here. But here, and syngas will be leaving through the top. But in this, both the biomass and the oxidizing agent is going through this direction, and syngas is taken from the bottom. And another thing is, here we are using higher gasification temperature, around 1100 to 1400. So comparing to fluidized bed, this is a very high temperature, because in fluidized bed it will be around some 600 degree to 900 degrees Celsius. But here we are having a gasification temperature of 1100 to 1400 degree Celsius, and they are very much suitable for large scale plants. So that is the advantage of these entrained flow gasifiers. They are suitable for very much large scale plants. But the thing is, they require a fine and dry feeds. So moisture content should be very less, as well as this particle size should be less. And the main advantage is they will not have any tar. So tar content is eliminated, and also less CO2 and methane. So mainly biomass, this syngas will contain carbon monoxide and hydrogen. And what is the particle size here? Particle size should be less than 1 millimeter. So if you compare fluidized bed and entrained flow gasifier, we have a lot of difference. One is the flow direction. In fluidized bed gasifier, the air or oxygen was feeding upward, but here both the biomass and the oxidant are feeding in downward direction from the top, and gas is taken outside. That is the one difference. Then we have this temperature difference in temperature. The entrained flow gasifier is use high temperature, and they are very much suitable for large scale plants. Fluidized gasifier is suitable for some medium scale plants, but the entrained flow gasifier is very much suited for large scale plants. And they don't have very less tar problem, and CO2 also reduced. But the disadvantage is we have to be very careful about the biomass. So biomass should be very dry and very smaller in size, that is less than 1 millimeter. So particle size of biomass should be less than 1 millimeter, and moisture should be less than 15%. Now we have another type of gasifiers, that is a plasma gasifier. So we are studied about the plasma state, that is the fourth state of matter which exists in very high temperature. So that temperature we are reaching in plasma gasifier. So this is a typical plasma gasifier. And the important thing is, in plasma gasifier they are immaterial about the biomass or whatever waste it can take, and its size also that not that much important. Size or moisture or composition, that is immaterial, because we are converting into a fourth state of matter. That means that much high temperature we are generating. So these are very much suitable for some typical waste, not only biomass, some waste conversion. So what is the basic idea? Here we are using a plasma torch. So you can see here a plasma torch is used in this for obtaining high temperature, and they are powered by an electrical arc between the two electrodes. So we are using two electrodes, just like welding. Here also we will be using two electrodes for producing an electrical arc, and then that arc is used for creating a torch with the help of some gas and inert materials. And we will be using this plasma torch for getting high temperature. And typically that torch temperature will be some 2000 degree to 14,000 degree, and gasification temperature, so you can see here it's very high gasification temperatures. See, in the fluidized gasifier it was less than 1000 degree. In entrained flow it is around 1100 to 1400 degree, but here you can see in plasma gasifier these are very high temperatures, that is 4000 to 7000 degrees Celsius in this gasification zone. And the main advantage is we can convert any hazardous compounds into elemental constituents, and the main composition of syngas will be only H2 and CO, that is hydrogen and carbon monoxide. And this is the most attractive part, that is a particle size, moisture content, composition. These are not matter for a plasma gasifier. So that is why these are most of the countries are going for this, for converting waste to syngas, because these are not only useful for biomass, but they can be used for converting medical waste, plastic waste and metallic waste, etc. So anything we can mix and feed into the gasifier, and the gasifier will convert into hydrogen, mainly hydrogen and carbon monoxide. So that is the advantage of plasma gasifier. Of course you have to spend a lot of energy here for producing plasma torch, but still this offers a method for converting the waste so that we can reduce the landfill, etc. And this metal slag we can take outside from the bottom and we can reuse. So these metals can be recovered from slag and reused for some construction or other applications. So that is the idea of plasma gasifier. So mainly we are converting in or working in the plasma state with the help of a torch created from an electric arc, and we are using mainly very high temperature. That is the important thing is this gasification, this plasma gasification does not depend on the particle size, so we can use smaller materials as well as larger. We can use any waste, plastic, medical waste, or any harmful hazardous waste. So that is why these gasifiers are very much attractive in today's waste mitigation. So we will discuss this in another session. So thank you.